this is joint work with Technical University of Darmstadt, Sanctuary, which is a spin-off, Radboud University in Netherlands, also TU Delft, and University of Zagreb. I need to press the, yes, okay. You all in this room know that fuzzing nowadays is a quite mature research direction, and we had a lot of key drivers for adoption also in practice. We had, for example, enabling technologies like firmware rehosting, emulation, to get much more targets fuzzed. But we also had, like the previous talk explored, we also had platforms supporting this adoption, like OSS fuzz. And we also had a lot of technical improvements. For example, in fuzzers, we have stuff like fast snapshots or hardware-based coverage tracing. But we also had algorithmic improvements. And the nice thing about algorithmic improvements within a fuzzer is that they're actually highly portable. So for example, coverage tracing might be very hardware dependent, but algorithmic improvements you can easily transfer to new fuzzers. Let's get a bit of a definition straight on this talk. So a fuzzing technique is usually some kind of dynamic testing where it applies random inputs, which we call test cases, to a target to see if it crashes. And we have a kind of historic separation into grammar-based or generational and mutational fuzzers. So grammar-based fuzzers usually, as the previous talk explained, use some kind of structured definition of input and try to derive new inputs, whereas mutational fuzzers use biology-inspired mutation operators to modify the initially provided seed test cases. So how does such a mutational fuzzer look like? This is a bit based on AFL, but it's actually quite, I would say, adoptable by most of the mutational fuzzers. Usually you have some kind of deterministic stage in the very beginning, which is a predefined set of operations that you apply to your input. And then you have a so-called havoc stage, where you actually, for a given time per seed, randomly apply mutation operators based on some kind of statically defined probability for each operator. And next, for some fuzzers, you also have a splicing stage, which, same as the biology operators, recombines two test cases to form a new test case. And because some of these stages are rather costly in terms of compute, you can also skip some of them at runtime. And there's also fuzzers that leverage feedback from reapplication, for example, new coverage reached, to further steer this process. So in that picture, what is actually a mutation scheduler doing in this case? A mutation scheduler is a new component in this process, which hopefully, optionally takes feedback from the execution and tries to adapt this probability vector for the different mutation operators in the havoc stage. There's also previous work in this area. So mutation schedulers, a pretty popular paper was mopt at Usenix in 2019, which used a variant of particle swarm optimization. But there's also not only papers tackling the challenge of which mutation operator to schedule next, but also where to apply it. We call this location optimization approaches. There's some very popular approaches like taint tracking, but also more lightweight techniques that got established a bit later. And we grouped another important research direction, which you call other scheduling approaches, which, for example, consists of seed scheduling, which tries to find some kind of optimal energy distribution. So how long does a seed need to be fuzzed? But these all have some kind of drawbacks in practice. For example, for previous papers in the mutation scheduling area, it was very hard to show improvements in practice. And they also introduced new per target parameters that you had to fine tune based on your target, which made adoption in practice quite hard. Then you also have shortcomings on the location optimization side, because usually you want to optimize both, so location and operation. And they can be expensive to compute and also expensive to integrate. So for example, for taint tracking, you need to really track the hot bytes in your fuzzing process. And for other approaches, you might need to statically generate additional information. Finally, for the other scheduling approaches, they usually target a very early step in the fuzzing loop. So it might be that some kind of contradictory effects get applied later, but they are highly interesting to combine them with other approaches. So what do we do in DARWIN, which is our mutation scheduling approach? This is like a zoomed in picture into a regular Havoc stage, which you can also find it like in AFL. You have mutation operators, for example, in this case, bit flip and overwrite bytes, but in reality, you get much more. And we just made up some numbers and statically assigned probabilities. But now at runtime with DARWIN, we fine-tune these probability vectors for the individual mutation operators, not only statically, but we readapt over time. For this, we leverage coverage feedback, which we get from the target program anyway, and then optimize and give this new probability distribution. So how do we optimize this probability vector? We use so-called evolution strategy, which is actually a pretty simple algorithm from optimization, from the optimization field. You see on the left, this is our probability vector for the different mutation operators. You randomly generate such a vector, and then you have a so-called perturbation operation, which is also just a mutation, but we had to call it differently for a definition reason. And this perturbation actually modifies a single entry in this vector and generates a set of children based on this parent. And then you define some kind of fitness function, which in our case was the number of new unique paths, because this is quite a number that you can efficiently get at runtime. And you see which of the children solutions actually evaluates best in regard to this fitness function. And if we found such a child, this will be the next best parent in the next iteration. And you just continue this throughout the fuzzing campaign. So as I said, this is a very simple and efficient algorithm, but it's also a very local algorithm, which means if your algorithm found some kind of local optimum, it will likely be stuck in that optimum. The perturbation is not enough to actually get out of this again. So our solution for this was introducing more parents and more children as a consequence. So this is what we call the multi-parent evolution strategy. Usually in the literature, you will find the definition that you refer with mu to the parents and with lambda to the children. And anecdotally, also in the literature, you will find that 5 parents is best and 4 children is best, full stop. And we also did some kind of preliminary evolution evaluation, and this indeed turned out to be true. And then again, during the fuzzing campaign, you cycle through these best parent solutions and further evaluate your children's solutions. And based on these percentages that you have for every mutation operator, it can be a bit costly at runtime to evaluate. So we did a performance optimization, which in this case is changing the representation of this vector to a binary representation. So for every mutation, you just say, you just store the information whether it should be scheduled or not scheduled. Which means that DARWIN is actually the very first mutation scheduler to leverage this quite simple algorithm to optimize mutation scheduling. But it has a tremendous advantage compared to the existing related work, because it manages to keep execution speed high. And another important approach for practice is that you don't have any target-dependent parameters. You can easily adopt it as a drop-in solution. And we also try to keep this easy adoptability by making it very simple to integrate in our implementation. So what was it worth in the end? We tried to do a very systematic evaluation. And of course, the first thing that arises when you do such kind of an evaluation is was the actual initial assumption on the problem actually correct? And in this case it was, is mutation scheduling a dynamic problem? Or can I just take some pre-optimized static vector per target and I'm done? And further, it makes sense to see if it really is worthwhile to trade in speed for efficiency in that stage. And of course, also the usual stuff you will find in probably any fuzzing paper you read nowadays. So coverage, time to coverage, which we won't cover in this talk now, and also bugs. So did we find new bugs? How good was it in finding bugs, and what's the time to find bugs? First on like a coverage experiment, but with a specific focus. So we did our coverage setup based on bin utils, but also on other targets used in related work, and repeated it on 10 runs for a 24-hour campaign. And we saw that edge coverage really shows there's an improvement over baseline, but also related work. More important for us was we also tested like the static versus dynamic problem by pre-optimizing a vector and then loading it in the next fuzzing campaign to see how it performs. And there we also saw that there's a relatively big improvement over the static variant, which you can also see in these two examples. I have to say, I picked up these two examples from the paper because I found them the most interesting, actually. So size is, let's say, a target where it really worked well, while in CXX filled, it worked not so well. The question is, why was it the case? And it actually was the case because CXX filled and also some other benchmarks, which we'll see in the next slides, require highly structured input. And for this highly structured input, we see that DARWIN, as well as mopt actually, reach a very local or global optimum quite early. So this are, we call them mutation histories. This is basically which mutations have been scheduled between two coverage points. Then you can see that in both fuzzers, actually, the distribution is quite stable after already 20-25 minutes. So this means the optimum has been found super early, and in the next time you're just wasting your cycles on further trying to optimize, but you're already reached the global optimum. Whereas on the more positive example on size, you see that this is actually some kind of ongoing process. So it's not really finding the global optimum in the first time and stays there, but keeps reiterating. And there we also see like a much better benefit from this efficiency increase. Then we also run a FuzzBench campaign, which is now very demanded when you do a fuzzing evaluation. There we also had an improvement based on baseline and related work. But again, what was more important was for these highly structured input, we again saw that mutation scheduling was actually preventing further advances here. So we went on to finding or doing some kind of controlled crash experiment. In this case, we based our experiments on a paper called Magma, which is a benchmark suite to find backported bugs in popular applications. It offers actually a variety of reports that you can generate. In this case, we took the survival analysis because it reflects the estimated time to reach a bug, which was quite interesting. And here DARWIN finds 15 out of 21 bugs the fastest among all fuzzers. But we also see that it has difficulties finding these lower bugs, or at least the Magma benchmark report says that the other ones can reach it within a quite long period of time. But this already shows that there has been like a large inconsistency between the different runs. So it's also not very likely that mopt or AFL will find this bug in every run. And we also did a final experiment on crashes where we used our coverage targets from the beginning. Here we denoted like two different measurements. The max measurement, which means the number of unique bugs we found within one run, and unique, which covers all 10 runs we performed. And here we can clearly see that the Darwin variants we implemented outperform the baseline as well as the related work. And notably, we also ported Darwin to EcoFuzz and can see also that it makes a huge difference in bug finding capabilities. And we also found a novel bug, to our surprise, actually in, I guess, the most well-fuzzed target ever in history. So it was a target in the bin-util suite, it was object copy, and it was a memory leak, which was unfortunately not exploitable. And with that, I'd like to conclude my talk. Darwin is actually the first evolution strategy-based mutation scheduler. We can show that the problem is actually an adaptive problem, and we have a significant improvement in bug finding capabilities while maintaining this easy portability and usability in practice. Thanks.
Can we please go back to your presentation on mutation history? I had a hard time to understand.
Can we switch to? Yep, perfect.
Mutation history, yeah, exactly.
Yes.
The failure, the CXX field. Would you be able to go over that case again? Like what is happening here? Why Darwin can't?
So when you reconsider these multi-parent solutions, they are in the beginning, they are highly diverse. So they're randomly generated vectors basically. And then they're adapting over time, so they are more or less getting closer to the optimum. But then we see that there's actually some kind of stalemate situation where it found the global optimum and it's not shifting anymore. And then you're continuing to waste cycles on this optimization problem.
You're reaching global optimum and then you're revolving around that, right?
Yes, yes. In practice, that is probably what's happening here, yes.
But then how does AFL work around that, or does not?
Yeah, the thing is that AFL is just randomly choosing these mutations, right? So it doesn't actually waste any cycles on further optimizing anything because it's not optimizing. So this is also why you see on AFL that the distribution among the mutation operators is also completely uniform, right? They're all the same size.
Thank you. Thanks so much, Patrick.
Yep.
Cool. Other questions? I'll take a closer one first.
Hi, Andrew Searles from UCal Irvine. So kind of following up on that question, I was wondering if you had considered anything about once you've found a global optimum, stopping the optimization process to make it more efficient.
That would actually be an interesting idea. Yes, thanks. But we haven't worked on that so far. But I think it would be very interesting in the future work, yes.
Thank you.
Or at least lower the amount of energy spent, right? Instead of training every round, like do this every couple of rounds and then do something like a...
Maybe to add, I mean, this is also what I mentioned a bit in the beginning, like the interplay of different scheduling solutions, seed scheduling and mutation scheduling will be interesting in the future, yes.
Hi, Alexander Bulyeko from Boston University. So if I understood correctly, you're weighting different mutation strategies. Some like recent fuzzers have looked at like weighting individual bytes within the input. So for example, focusing your bit flips around a certain amount of bytes that seems to provide the largest coverage or the largest like value profile coverage. So I'm wondering, like, with that, it seems like your input space grows a lot. So have you thought at all about how you could apply this technique to those sort of spatial fuzzy mutation techniques?
Yeah, if I understood your point correctly, you're saying that, so you're referring to this location optimization. That's what you call in the beginning, right? Yeah. This I also mentioned in the beginning. I think it also makes sense on combining these techniques.
Are they orthogonal?
Yes, hopefully, they should be completely orthogonal, but it would need some proper evaluation to show that they are orthogonal and there is indeed a synergy when you combine them.